Hello everyone, welcome to the class once again. I hope you're all doing good and you're in the best of your health. Hope you have seen the last lecture and hope you have understood the method of conduction and how conductors are connected in series and parallel. We have seen in last class that the heat resistance, or while calculating the heat current, heat resistance is very much helpful. Conductors in series, if they are connected, then the net heat resistance is sum of heat resistance of individual conductors. And when conductors are connected in parallel, the heat resistance is evaluated by 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2, and so on. As many conductors are connected, you can go on adding it. You can remember the same formula by using the concept of electric current. And then you can evaluate the heat current through any conductor while they are connected in series or in parallel. Now let's go ahead with today's class with a small illustration and then further go ahead understanding the concept of transmission of heat through convection. Let's understand growth of ice. Now see, let me tell you, you will be finding that ice layers are formed on lakes in very chilly winters. You must have observed ice layers are formed in lakes in very chilly winters. So let's say how this growth of ice depends on time that will take, what layer or let's say what thickness of ice will be formed as time passes on. Now see, I am drawing here a normal lake. How will it look like? This is a normal lake that I am drawing. This is the bed of the lake and it will be entirely having water within it. So let me draw water layer here. The bottom part of the layer will be having water and the above part will be having ice over it. So let me show you that above part is having a thick layer of ice, as you can see in this diagram. The above part I have drawn, this is a thick layer of ice that has been formed here. Let me show you, this is a thick layer of ice that has been formed. Now with what rate this thickness is increasing? With what rate this thickness is increasing? Let's try to find out that. Now imagine any small layer. See what I'm going to do, I'm going to draw a very small layer. Imagine a very small layer of thickness dx. Imagine a very small layer of thickness dx. Let's say this is what I have shown you here. So this length was x, this thickness is dx. Now let's talk about the temperature. Temperature just below the layer of the water will be 0 degrees Celsius. So let me mark this temperature T1 is equal to 0 degrees Celsius. Now temperature above the layer or above ice shelf will be lesser than 0 degrees Celsius. Then only heat will be further radiated from the ice. You see here temperature, let's say it is T2, which is actually in minus, so let's say this T2 is equal to minus theta degrees Celsius. Let us say T1, the inner temperature, although it's 0 degrees Celsius, it's higher than the external temperature. So what will happen? Low temperature, high temperature, heat is going to move through this part. So the flow of heat will be taking place as shown. This will be the direction of flow of heat. This is the sense of flow of heat from the layer of ice. This was the ice shelf that I have made here. Now, if I write about what is the rate of transmission of heat through this layer of ice, so we can write dq by dt, rate of transmission of heat, is equal to K, where K is the, let's say, thermal conductivity of ice, and A is the area of cross section, Ka T1 minus T2. So we want to write 0 minus theta, and let me make here a big bracket. That will be good for us. 0 minus theta. So this formula will give us to evaluate with what rate the heat is flowing divided by this length, that is x. This is what we got. This is the length x, because length that we have considered, that is x, and the small part we have taken, you will understand why that part we have taken now. Ka 0 minus theta by x, if I simplify it, I'll be having K Ka 0 minus minus theta, you're going to have theta by x. This is equal to dq by dt. We got this. Now understand, for any small part whose thickness is dx, if you want to mark it, if you want to know what will be the amount of heat coming out to convert this part into ice, the amount of heat that would be radiated to convert this thickness dx into ice. So amount of heat radiated should be amount of heat released from the ice layer to make that thick part. Let's say its mass is m. Let's say its mass is m. So what I'm going to do, I'm going to mark its mass as small m. So what we're going to have, mass or amount of heat released to make a ice layer of thickness dx, that will be equal to dq, that is equal to m into L. Now mass is what? Mass is rho into volume, where rho is the density of ice shelf that you're talking about. That is rho into volume. So let me write this as rho into volume into L. L is the latent heat of fusion of water. Let's go ahead with further simplifying it. Rho into volume. Volume you try to understand. That will be equal to A into dx. So let me write this as rho A dx into L. We got this. Rho A dx into L. This is the amount of heat that should be released from the ice so that dx thickness of ice layer is formed. Now dq, you see here dq by dt is k theta by x. Now if I replace, here you see dq by dt, here we have dq this. So can we write an equation? Let me use this part of board. I believe that you would have seen this diagram and you would have understood. Let me write this part. Let's go ahead. dq by dt is equal to k theta by x. If I write dq as rho a dx by L, so what I'm going to write? I can write from this equation number 1, we can go ahead and we can write dq is equal to k theta by x dt. From 1, dq is equal to k theta by x multiplied with dt, and from equation number 2 we have dq is equal to rho a L dx. So let's go ahead, let's write it as dq is equal to rho a L dx. Equation number 1, equation number 2, we have simplified both and we have written here in the most simplified manner. Can we write, equating both the two, can we write ka theta by x dt is equal to rho a L dx? Not a problem, simple one. Rho a L dx. This is the line of separation. Now see, if we take only dt part at the left hand side and rest of the part in the right hand side, see what we are going to have? We are going to have dt is equal to rho a L dx into x divided by k theta. So rho a L divided by k a theta multiplied with x dx. So a has got no role to play. Let me cancel out this area of cross section term. So rho L by k theta into x dx. So we got a very simple equation. Let me rub this part. I believe that you would have taken down this one. And don't worry, if you have taken down, I will give a quick recap of the entire derivation that we are doing. So we got dt is equal to rho L by k theta, rho L by k theta. Remember, k is thermal conductivity, that is the coefficient of thermal conductivity, k theta into x dx. Now, if we integrate within proper limits, then we will get a final relation between time and the thickness of the layer formed. You see here, from time 0 to t, if I integrate for time 0 to t dt, this equation, see what I'm going to have? I'm going to have rho L by k theta as constant, here x dx, 0 to any finite value of x. So we are going to have here t is equal to rho L by k theta integrate this, you will get x square by 2, 0 to x. Proceed from here, rho L by k theta, x square by 2, 0 to x. Go ahead, substitute the value. Rho L by k theta, x square by 2 minus 0. So finally x square by 2 you are going to get. So time relation that you are getting, time t is equal to rho L by k theta multiplied with x square by 2 is what you are going to get as time. Now see, within some from 0 to t, the thickness of layer form that will be related with time t as per this equation, rho L by k theta x square by 2. For some definite time from T1 to T2, if you want to find out what is the thickness of layer that has been added, for that what we need to do, for some definite time, to see here, if we write dt integrated from T1 to T2, any two time interval, and then if we write the same thing, rho L by k theta x square by 2 we got. Here we have to put the limits only x1 to x2. So what we are going to have? We are going to have t2 minus t1 is equal to rho L by k theta. Now x2 square by 2 minus x1 square by 2. We got this. Now we can substitute the value of x2 and x1. If you simplify this equation, we can write T2 minus T1 is equal to rho L by 2k theta in bracket x2 whole square minus x1 whole square. Now let me sum up this entire relation that we have obtained. This is the value of T2 minus T1. Within any definite time period, the thickness of layer added that will be proportional to, see here, x2 is the final thickness, x1 is the initial thickness, so their difference is x2 square minus x1 square, that will be proportional to the time. This is what we have obtained. One equation is this. Now for the entire ice layer, you can use this equation, time t equals to rho L by k theta x square by 2. This formula, these two formulae actually entails us in understanding in what time a definite layer of the ice will be added up in the ice shelf that is above the lake. So what we started with, there's a lake, it's freezy winter there, the upper part is actually covered with ice. With what rate the thickness is increasing, in how much time this will go on increasing. Above temperature is lower than 0 degrees Celsius. Here temperature I am taking as 0 degrees Celsius. So heat will be released. As heat is released, what we have taken a layer of ice shelf as x. Its area of cross section we have taken as a. This thickness, small thickness we have considered, that is dx, that will be added up. Now see here, we went ahead with the equation with what rate the heat is coming out. So dq by d theta is equal to ka 0 minus theta divided by x. We went ahead, we also framed that what is the amount of heat needed to be released to make an ice shelf of thickness x. That will be equal to dq equals to mass into length. The mass was given as rho into volume. Volume was given as a into this added part, that is dx. We wrote this, then we went ahead, we equated dq and dq from both the equations. Then finally we got a relation between time and the thickness of the layer that has been formed. This is how you can evaluate for the thickness of layer of ice that has been formed in this case. Let's proceed with the next one. So if any question comes based upon with what rate ice is added up or ice is formed, or with what rate it is growing, what is the thickness of ice layer which has been forming, in this case you can evaluate in this way. Let's proceed from here and let's go ahead with the next part. Now let me sum up the entire part of thermal conductivity based upon conduction we have done. How conduction takes place, how heat is transmitted using the process of conduction. Remember, it's possible only in solids. Some solids are good conductors, some are bad conductors. Generally, metals are good conductors of heat, non-metals are bad conductors of heat. Metals such as iron, steel, then you can think of more copper, all these are good conductors of heat. Non-metals, wood, plastic, all these are non-metals which will be actually bad conductor of heat. Let's go ahead. We also very many practical applications of this concept of conduction. Now further, we also saw about the series combination of conductors and the parallel combination of conductors. Now after completing the concept of conduction, let's go ahead with the next part of heat transfer, that is through convection. Let's talk about convection. Now see, convection is a very natural phenomena. Every day we observe this. Now have you observed that what happens that when it starts getting, the days start getting with time, it from morning to the afternoon to the evening, what happens? The sun shines and the heat in the atmosphere increases. Now how the air of the atmosphere gets heated up? It's due to the process of convection. Try to understand this. Now see, I'm going to draw entire atmosphere. The atmosphere would be comprised of air layers. So what I'm going to do, I'm just completing the entire atmospheric layers of air. From up, the sun is shining, its rays are falling and it is heating up the atmosphere. So what is happening? First of all, the lowest part is going to get heated up. Try to understand, this part will get heated up. It will absorb the heat energy. It absorbs heat energy, or let's say it gets heated up from the heat absorbed or heat obtained from the ground. Now as it gets heated up, it will expand. Its density will become low. And as its density becomes low, it will start rising. It will start rising in the upper layers of the atmosphere. As it starts rising, what will happen? The cooler air is going to come down. So cooler air, cold air from top, it will come at the bottom part. So gradually this space is vacated. Now to fill up this space, cold air from top comes here. It's going to occupy this leftover space, and this part is going to be vacuum, or let's say there will be no part of air here. Now what happens? Gradually warm air is going up, colder air is coming down. Now again this cold air which has come down, it will get heated up. Then again its density will decrease, it will rise up, the colder air will come down, and gradually this process is going to continue. And finally a uniform state will be reached when the entire atmosphere is heated up. This process of heating up of atmosphere, this is done through convection. Heating up of atmosphere, the process that we are observing, that is through convection. Heating of atmosphere, that is through convection that we are observing in this case. Convectional currents are formed. They are circulating. They are actually changing the positions, and due to it only we find that regularly or gradually the entire atmosphere gets heated up. More where you are going to find the concept of convection. See, this was a small example of convection. Convection currents are formed here. Which are other places you are going to find that convection process is taking place? Let's go ahead with a very simple example. At home, you would have sometimes boiled water. If I take water in a container and if I start heating it from beneath, so what I'm going to do, I'm going to lit a flame from bottom, and I'm going to observe how the water gets heated up. Let's say here we have a flame. Now as the water gets heated up, first of all what will happen? The bottom part gets heated up initially. Initially it absorbs heat. Now what will happen? As it absorbs heat, its density is going to decrease. Initially it absorbs heat. As it absorbs heat, its density is going to decrease. So what will happen? The warmer part of the water, the warm water, is going to rise up. So let me draw a chain depicting it. So the warmer water is going to rise up. There will be a space that will be created here. There will be space that will be created here. To fill up this space, the colder water from top will come down. The colder water from top is going to come down and it's going to fill up this space. Warm water went up, cold water came down. So a convectional current is being set up here. Now entire beaker or entire volume is heated up through this process of convection. So again what we are finding that convection current is set up, which is actually heating up the entire volume of water. Convection current is set up responsible to heat up the entire volume of water. Hope that you would have understood the concept of convection, and after this we will be finding that there are many places where it is applied. Applications, or let's say day-to-day observations. First of all, applications of convection current in our day-to-day life. Have you ever seen or have you ever come to know about land breeze and sea breeze? Formation of land breeze and sea breeze. I am not getting into detail of what is land breeze, what is sea breeze. Land breeze and sea breeze. Now, water has a very high specific heat capacity. Now, when sun shines during daytime, what will happen? Land will get heated up very soon, and water in the oceans or in the seas will not get heated up that fast. It has got a very high specific heat capacity. That means to raise its temperature, it requires more time or more amount of heat energy. You can think of in this way, more amount of heat energy is required to raise its temperature through 1 degree Celsius. Land will get heated up soon. So if I try to draw a diagram, let's say here we have sea or ocean, that is water part, and let's say here we have the land part. So this is heated up quickly because sun is shining during daytime. This is heated up. The oceans and sea, it will remain cool. When it is heated up, that means what will happen? That means a low pressure region will be created here and a high pressure region will exist here. So air is going to blow from this cooler part to this hotter part. This is what we are going to observe, the phenomena of air moving from sea to land during the day hours. But just reverse happens during night hours. So let me go ahead and let me tell you about what happens during the night hours. In night hours what happens? Land gets cooled up very quickly, but same doesn't happen for the oceans and seas. During night hours, let us talk about the convection process that is taking place due to difference of heat at the two parts. During night hours what happens? Suppose this is the sea. Even sea doesn't get cooled up quickly. If it doesn't get heated up quickly, it will not get cooled up quickly. So this will remain hot, and the land part that we are observing, this will cool down very quickly. So a region of low pressure will be existing above sea. A region of low pressure would be existing over sea, and a region of high pressure would be existing over land. This is what we are going to observe. So high pressure, low pressure, so the winds are going to blow in this direction from land to sea, because it finds a low pressure region here, so wind is going to blow along this direction. This is what happens during the night hours. So this was all about the land breeze and sea breeze. Now let's go ahead. Other kinds of practical observations in our day-to-day life. Now see, you must be knowing about trade winds. Trade winds also blow due to difference in pressure of the two regions. You must have learned in geography about westerlies, easterlies. Westerlies, the winds that are coming from west to the eastern part of our nation, and easterlies from the winds that are blowing from eastern part to the western part of our country. The trade winds that generally blow, that is also due to convection, because there's a difference in pressure due to difference in heating of the two parts of the land. Hence, trade winds blow, that is westerlies and easterlies. More observation, monsoons. We know that from the month of June, monsoon enters India and it showers all across our nation. Why? Now see, first of all, the explanation of monsoon is given by differential heating between land and sea. And what happened? The land gets heated up, a region of low pressure is created over land, and the winds blow from sea to land. This was the first method to actually give the reason for monsoon winds. Again, that is due to the conventional current that has been formed due to differential heating of land and sea. Let's go ahead. So this was all about convection. Convection, see, actually what is happening in convection? Convection, the molecules of the matter are moving from one point to other. As I've told you in the demonstration that I've given you, the entire molecule, the entire substance was moving from the lower part to the upper part, and hence convection was taking place. Now, this was the natural convection that we have studied till now, because you need not to force it. This will happen due to gravity. Natural convection. Why? Because it takes place due to effect of gravity. Less dense, that is going to move up the warmer air, and cold air more dense, so that is going to be attracted by earth with more force. It takes place due to gravity. Need not to work upon it. So this was all about convection. Now, let me ask you something. You all must be having a refrigerator in your house. You must have seen the ice shelf in your house, in the refrigerator, that is placed at the top. That means we have the colder part at the top. What happens? That is going to coolify the entire air within the refrigerator. The colder part from top, that's going to come down because of its more density, and then warmer part will go up so that it will be coolified. So this was all about the convection that is taking place in the refrigerator. So I believe that you would have understood the concept of convection, and I want you all take note till here so that I may clear the board for the next topic. Now hope that you would have understood the concept of convection. That's quite simple. And what happens in natural convection? Automatically the warmer part moves up and the colder part comes down. So this is what we have observed in natural convection. Now there is one more convection, that is the forced convection. Forced convection, what happens in this? Sometimes the warmer air is made to move through a pump or a blower in opposite sense, whereas it's going to occupy the colder part, but then too the pressure at that part will be high, but then too you are making to move warmer air from low pressure to high pressure, because you are using a pump or a blower to actually pump the warmer air from the region of low pressure to region of high pressure. This is made due to a pump or a blower. That means a motor is used. Now, forced convection also takes place in our body also. Our body has got a wonderful mechanism to regulate its temperature. The temperature of the body is maintained by blood streams moving in our body. Now, heart actually pumps up the blood, and that is responsible to maintain the temperature of our body. And that is also due to the forced convection that is taking place in our body. That's one example. You can write it down separately. To regulate the temperature of our body, forced convection is taking place. Now let's go ahead with the next topic, that is the next method of transmission of heat, that is radiation. This is the most important part of this chapter, radiation. Now, although you all must be knowing about radiation, radiation are what? These are just same like electromagnetic waves, these are like light waves. These radiations are like, they are electromagnetic waves. Electromagnetic waves, that means they are like light waves. That means they are like light waves that we find near us. Next thing, That means they are going to show all the phenomena those are given by, or those are shown by light. That is, they are going to be reflected and refracted. They are going to be reflected and refracted whenever they interfere any medium change. This is all about the radiation. Now some more parts. What do these radiations carry with them? They carry heat energy. Now radiation transmission of heat can take place, that is, transmission of heat through radiation can take place in all the three states of matter, that is solid, liquid and gases. So transmission of heat that is taking place through radiations, that is possible by all the three states of matter. So it takes place in solids, liquids and gas. Takes place in solids, liquids and gases. This is what we are going to have, solid, liquids and gases. In all the three states of matter, the transmission of heat can take place through radiation. Now radiation is carrying some heat energy with it. As it passes through the environment is going to get heated up. So nearby atmosphere gets heated up. Example, there are a lot of examples of radiation that we see in our day-to-day life. Now, I know that you are all grown up, but let me tell you, and you all must not be using incandescent bulbs. The bulbs that you are using these days, those are CFL or LED bulbs that are very much energy efficient. In very low power, they are giving us more amount of light energy. But let me tell you, when I was very young, at that time we used to have incandescent bulbs. Those are very high power bulbs, but they were emitting large amount of energy. A lot of amount of heat energy was actually lost and that was wasted. Now, what was the mode of transmission of heat energy through all those bulbs? It was all due to radiations. Now in winters, what you do? You take a heater, you see a coil burning within the heater, that it actually glows up and you finally find that the nearby atmosphere gets heated up. Why is that so? The light that is coming from heater, that is warming up the nearby atmosphere. So let's go for examples of radiation that we are going to observe. Examples. First of all, in winters, heater. What happens if I try to draw a heater? See, a heater will be something like this. It will be having a rod in which a coil would be, although let me draw a straight heater, that will be far better. I try to show you the tilted one because the heat was transmitted through it. So we have a heater, we have a rod within it. Now what we see, we find a coil is present within this rod. I hope that you all would be clear of this diagram. Now as the switch is made on and as this glows, we find that the entire nearby atmosphere gets heated up. So that is all due to the process of heat transmission through radiation. So let me go ahead, let me show you how heat is transmitted. The radiations gets it is transmitted along each direction. So the entire atmosphere gets heated up. So because of radiation, we find that the air molecules near to it will get heated up. It also falls on your body starts acquiring the heat energy, you feel the heat due to this heater, and the energy that reaches you, that is all due to the radiation that is reaching up to you. So this was all some examples of radiation. Now even in your school trip, you would have certainly gone for a bonfire. You would have lit a bonfire and you sit quite far off from the bonfire, but then you can feel the heat energy coming from the bonfire. Now from where does that heat energy comes? The heat energy that reaches up to you, that is all due to the radiation. Now in this chapter, let me tell you some important points. We have talked about conduction and convection. Conduction, we saw a formula for flow of heat. Convection, there was no formula involved, but you should know the process. In radiations, we have formulae that will be very much useful to calculate questions, to actually solve some questions. There are absorptive power, emissivity, and Kirchhoff law, Newton's law of cooling. So many applications of this concept of radiation. Then we have Wien's displacement law, Stephen Boltzmann law. We have all this law, which will be very much useful in the understanding more detailed the concept of radiation. We have a lot of things to understand in this topic of radiation. I believe that the basic thing about radiation would be clear to you all, and let us go ahead with the calculation part in the next class from today. So I believe that you all will be revising after each of the class and you will be practicing questions. After this class, I'll meet you in the next class with more concepts and with more detail of the concept. So thank you everyone. Wish you all the very best. I'll meet you on the next class.